So let's just talk vectors. We'll kind of move through it quickly since you've already read about it and discussed it a little bit, but pause me if you have questions, okay? So, scalars and vectors. When we measure quantities in physics, they can either be scalar or vector. So a scalar quantity would be any quantity that has a magnitude but doesn't have a direction. Like when we talked about speed or volume, or if you're counting a specific number of items, okay? Or if you're saying something, if you want to double something, those are all scalars, okay? So they don't have a direction, they just have a magnitude. And then the book anyway, is going to represent these with an italicized symbol. If you have a vector, then that quantity has both a magnitude and a direction. So that's like displacement, velocity, acceleration, things like that, where you are indicating both the strength or the magnitude of the vector and then also which direction it's moving in. And your book represents these with bold symbols. If you see people writing these down, a lot of times if it's a vector, they indicate an arrow over it. So that's just a little helpful hint there.
Do you have the guided notes?
In order to describe motion that doesn't go just in a straight line, which is mostly what we talked about in the previous chapter, just like moving in a straight line back and forth, you have to be able to use vectors because they help give you a angle direction. Okay? In diagrams, we represent vectors using an arrow, and the angle that the arrow is at is going to indicate your direction, and then the length of the arrow is going to indicate the general magnitude of your vector. So it's not always true that you can measure the length of the arrow and scale it up and get the magnitude of your vector. Sometimes, but not always. But they will in general, like a longer arrow means a larger magnitude. When we add vectors, you can only add them if they meet the following conditions. 1, they have to describe the same quantity. So if you have a vector for displacement and another vector for displacement, you can add those. If you have a vector for velocity and for displacement, those are not measuring the same quantity and you cannot combine them. And then they also obviously have to have the same units. So both of them are in meters per second, and you can combine them. Even if they're measuring the same quantity, if they're not in the same unit, you can't combine them. You would have to convert one of them in order to do that. When 2 or more vectors are added together, then the final vector that we get, we call the resultant vector. So if they are asking you to solve for the resultant, they're just asking you to combine vectors. Here's how we go about adding vectors graphically. So you want to do a scaled down version onto paper. So if you have something that's in kilometers, you could scale it down to, like 1 centimeter equals a specific number of kilometers, and then that would help you scale it down so you can draw it out. And that's when you would need to use a ruler to measure the length of your vector arrow, because you'd want it to be a match scaled down. Then you draw your first vector in the right direction with the correct magnitude. And then you're going to draw your second one starting with the tip of the vector, or with the tail of the new vector at the tip of the old one, and draw it from there. And then you can find the resultant vector by measuring from the tail of the first vector to the tip of the second vector. So in your book, they draw that kind of like, if you were starting here and ending here, but you went here and then here. Notice how the tail of one vector starts at the tip of the other, and so then your resultant would be from the tail of this one to the tip of this one. And then you can also measure the angle compared to, so for this one you would probably measure to the horizontal, and so then this would be your new angle to measure it. And then obviously once you find that resultant vector, you're going to measure it and scale up to get your actual numerical value, and then use a protractor to find the angle of the resultant vector. Just make sure that whatever angle whatever reference line you used to measure the original angle of the vectors you drew is the same reference point that you measure your resultant vector from, so that there's no inconsistency there. And then if you're finding the resultant of two vectors that are acting from the same point on an object, so say an object is moving over, like straight in front and then also to the left, those two vectors are acting on it from the same point, but you can move one of them so that the tail begins at the tip of the first, so that they form a triangle. Okay, so let's say you have you have your box that's moving in this direction and then also in this direction, and you want to find the resultant. You can move it so that you have, this and then this. That's a bad drawing. It would be more like if you had an object that was moving this direction and this direction. So then you can move it so that you have like this, because they're moving off of the same point, and then your resultant vector would be the path of its motion, which would look like this, right? This is only okay to do as long as you don't change either the direction or the magnitude of your vectors while you're doing this. So if you're moving them around, you need to make sure you're measuring correctly and not changing the magnitude, and you also need to make sure that you don't accidentally flip one and get it going the other direction, because that will obviously change your resultant vector. Then you'll measure the resultant vector as the third side of that triangle, use a protractor to find the angle of the resultant vector, and then you'll have your answer there. And we'll do some practice problems with this in a little bit. Some tips for working with vectors that your book gives is that if you have multiple movements, multiple vectors, that you're adding more than two, you can add them in any order that you want. Just, again, be careful of magnitude and direction. So any combination order that you want to do. And then if you're going to subtract a vector, you're going to add the opposite of it. So 30 meters west becomes negative 30 meters west, because it's the same as saying 30 meters east, but it's easier to subtract. And then if you're going to multiply a vector by a scalar number, you're going to end up with a vector still. It's not going to change it to be scalar. So if you're wanting something to go twice as fast, you're taking the scalar number 2 and combining it with multiplying it times your velocity vector, and then you're going to come up with a velocity vector that's twice as fast. So scalar times vector yields a scalar one. Same thing for if you wanted it to go twice as fast but in the opposite direction, you can multiply that by -2. So now you've doubled the velocity and changed the direction. Okay?